Good morning. My name is Fiona Parker and I'm an engineer from the Rolls-Royce Submarines business. Firstly, I'd like to thank RUSI and UK Pony for giving me the opportunity to present at this conference. I would also like to thank my colleagues at Rolls-Royce for their guidance. I would just like to clarify that the thoughts and ideas portrayed in this presentation are that of my own. The UK is currently planning, or at least proposing, to build 20 gigawatts electric of new nuclear power stations. This presentation looks back at the history of nuclear power generation in the UK and pulls out three notable trends which, if allowed to continue, would threaten the future stability of new nuclear build. The effect of the recent Fukushima accident will also be discussed. So Lord Hutton, you set the scene very nicely for my presentation. Please feel free to correct me if I get a fact wrong. This graph shows how the UK is going to lose approximately 1/4 of its existing electricity generating capacity over the next 20 years. This is primarily due to the closure of coal and oil-fired plants and the retirement of ageing nuclear power plants. Current peak demand for electricity in the UK is 60 gigawatts electric and is expected to rise. Therefore, unless new capacity is installed, a gap between electricity supply and demand will develop. Nuclear is well suited to closing this gap for many reasons, including its base load applicability. Additionally, the coal and gas supplying the majority of our electricity relies heavily on imports to the UK, often from geopolitically sensitive countries. Although new nuclear would also require imported fuel, uranium mostly comes from stable Canada and Australia. So in summary, new nuclear build can address the emergent electricity gap in the UK, increase energy security, and be effective at reducing carbon emissions. This graph shows when the existing PWR, AGR, and Magnox nuclear generating capacity in the UK will retire. The green area on the graph shows the proposed new build capacity reaching a maximum of 20 gigawatts electric by the mid-2020s. However, the scenario shown by the blue line requests 40 gigawatts of nuclear generating capacity by 2050, derived from the Department of Energy and Climate Change's 2050 Pathways Analysis report. This shows how the proposed new build, although okay for the short term, is not enough looking ahead to 2050. Further new build is required. New build therefore needs to be pursued at a reasonable pace of installation of sufficient generating capacity. The UK has a long history of nuclear power generation and research. It is important to examine this history to see if there is anything to take heed of to help achieve this challenging 40 gigawatt 2050 target. I'm now going to present three notable trends from the UK's nuclear past, which, if allowed to continue, would threaten the future stability of new nuclear build. Between 1970 and 1979, no new nuclear power plants were built in the UK due to an elongated period of toing and froing between what reactor type to build: a pressurised water reactor, a steam-generating heavy water reactor, or more AGRs. A PWR at Sizewell B was eventually given the go-ahead by the government in 1979, and it was intended to be the first of a programme of PWRs. But by 1995, all plans for further PWRs were dropped after a government review of nuclear policy. Today, inconsistent government support will delay new nuclear build, endangering the 40 gigawatt 2050 target. This is even more critical than previously because there will be no public subsidy for new nuclear build. The government therefore needs to act positively to provide the private sector with the confidence it needs to justify investment and to provide viable economics. Government support has indeed been positive and consistent since the 2006 Energy Review, but it must be recognised that nuclear requires a long-term commitment to be upheld in spite of electoral cycles. A mere 6 years' support is a drop in the ocean for nuclear. Moving on, programme overruns include the 20 years it took to build the AGR units at Dungeness B due to problems with the original design, poor project management and financing difficulties, and the 6-year planning application for Sizewell B, the longest ever in the UK. Additionally, unlike the French, the UK did not promote standardisation of design across the AGR reactor pairs, leading to future operational problems and reduced availability. To hit the 40 gigawatt 2050 target, we need a build rate of approximately 1 gigawatt per year, which is 3 times higher than the historical UK build rate. Programme overruns can therefore simply not be tolerated. Again, the government is taking measures to reduce the likelihood of programme overruns by improving the licensing process. The ONR is also working with Finnish and French regulators to understand design concerns ahead of EPR build in the UK. Furthermore, critical success factors for new build also include promoting design standardisation, design completion prior to construction, and the fundamentals of good project management and solid funding. A lack of forethought on decommissioning and waste management was also a feature of the past, leading to increased clean-up costs and neglect of facilities. This is embedded in a number of factors. For example, the organisations at the time had alternative incentives in either the pursuit of research or making a profit. Also, in the 1980s, decisions were made to continue with spent fuel reprocessing when it was uneconomical to do so, and past funding regimes to deal with decommissioning and waste management were ineffective. As a consequence, the UK now has a costly nuclear legacy to clear up, necessitating the creation and funding of the Nuclear Decommissioning Authority in 2005. The NDA requires substantial government funding, feeding public perception that nuclear can never pay its way. Today, there are moves afoot to avoid this past mistake. Plant operators are required to submit a funded decommissioning programme ahead of build. However, more can still be done. For example, with a geological disposal facility that the government has committed to, timely decisions on this are required so that plant operators can ensure their funded decommissioning programmes contribute sufficiently to its funding. With regard to nuclear stability, this presentation would not be complete without addressing the recent accident at the Fukushima Daiichi nuclear power plant in Japan. So, is Fukushima a concern? Has it introduced instability into the future of nuclear power generation around the world? Since only the 5th of May, Japan's single remaining operating nuclear power plant was taken offline, bringing the percentage of nuclear supplied electricity from 30% before Fukushima to 0%. To compensate for this, Japan has had to significantly increase energy imports, contributing to a record trade deficit posted in January this year. In Europe, Germany has decided to phase out nuclear power completely over the next 10 years, requiring substantial investment in its energy infrastructure. In the UK, there have been delays to the AP1000 and EPR pre-licensing activities. Parent utility companies E.ON and RWE have pulled out of their Horizon joint venture, and the NDA has decided to close the Sellafield mixed oxide fuel plant as it has lost its major customer base in Japan. However, there are still 60 nuclear reactors under construction in 14 different countries. The UK is also progressing with plans to build 2 twin EPR reactors, and what's more, UK public support for new nuclear build is now greater than that before Fukushima. With the global nuclear renaissance continuing at full speed, in my opinion, Fukushima has come at a timely juncture and can be used as an opportunity to increase the future stability of new nuclear build. The nuclear community has been reminded that it is key to get the design basis right. Reactors around the world are undergoing stress tests to review their readiness against extreme external hazards, and international organisations have vowed to increase cooperation on nuclear safety. Fukushima is also a prime opportunity to engage better with the public on nuclear safety and dispel the myths associated with radiation. The largest dose received by one Fukushima inhabitant was 23 millisieverts, according to preliminary data. This is the equivalent dose received from 2 CT scans. Does the public know this? Do they know what a millisievert is? How dose is received from a CT scan? More than likely not. Fukushima provides relevant context to increase public confidence in nuclear power. To conclude, I have shown that nuclear power is an effective way of addressing the UK electricity gap, increasing energy security and tackling carbon emissions. However, new build needs to be pursued at a reasonable pace of installation, as the proposed capacity does not yet cover the 2050 target discussed. 3 notable trends from the UK's nuclear past have been identified, which, if allowed to continue, would threaten the future stability of new nuclear build. On the whole, the UK is acting to halt these historic trends, but further effort is required. Lastly, although the Fukushima nuclear accident has caused some countries to abandon nuclear power, the global trend, the UK included, is to continue with new nuclear build. Moreover, Fukushima is a timely opportunity to make further improvements to an already safe sector and to provide better quality of information and education to the public to increase confidence in nuclear power.